Good day, everyone. On behalf of QSG, I would like to welcome you to today's webinar. QSG is committed to providing up-to-date, useful, and credible information on the topics that you care about. My name is Chris Skangas, and I will serve as your moderator for today's program. Today's webinar will be approximately 60 minutes in length. Charles will have a 45-minute or so presentation, followed by a question and answer session. If you have any questions during the webinar today, please use the Q&A feature or the chat feature, and I can ask those questions to Charles at the end of his presentation. So now I'd like to introduce you to the speaker for today. Charles Gillis has over 25 years of machine design experience in industry. He previously worked as a mechanical design engineer for Gillette, the Blades and Razors division of Procter & Gamble Company, where he designed automated machinery for manufacturing Gillette's blade and razor products. He has designed and put into service numerous pieces of manufacturing equipment consistent of complex mechanisms of precision assembled components. He has designed equipment to manufacture the Mac 3, the Venus, the Sensor 3, the Fusion, and Venus Embrace product lines. His consulting company helps clients with product design for assemblability and manufacturability, design documentation, tolerance stack-up analysis, and related capability building. For over 10 years, he has taught geometric dimensioning and tolerancing through Worcester Polytechnic Institute's Continuing and Professional Education Department. He is the author of Hammer's Blueprint Reading Basics, Industrial Press 2017. He is also a contributing author to Machinery's Handbook, Industrial Press 2020, Machine Designer's Reference 2011, and the CAM Design and Manufacturing Handbook 2002. Charlie earned his Bachelor of Science degree in Mechanical Engineering from Worcester Polytechnic Institute and his Master of Science degree in Mechanical Engineering from Northeastern University. He is a licensed professional engineer in the Commonwealth of Massachusetts and holder of a geometric dimensioning and tolerancing professional certificate senior level, or a GD&TPS, from the American Society of Mechanical Engineers. So without further ado, I'll turn it over to Charles for today's presentation. Thank you.
Thank you very much, Chris, and thank you everyone on the webinar for joining us here today. This is GD&T Advanced Concepts. And what I have on the screen here, these are the best ways to contact me after this webinar for a consultation on anything related to the topic of GD&T. So first off, why advanced? Well, even with an understanding of the fundamentals of GD&T, many professionals still lack the confidence to expertly and deliberately apply geometric tolerancing and to perform tolerance stack-up analyses to clearly define their product designs. Like with any language, this deeper understanding of GD&T is built off of the fundamentals. Thanks again for joining me for this webinar, for taking time in your schedule to learn a little bit more about taking your GD&T knowledge to the next level. What we call advanced GD&T at QSG is just part 2 of any GD&T training program. In the full training program, Advanced GD&T builds off the basics. We dive into advanced datum reference frame concepts. We thoroughly explore boundaries, what they are and how they're used. We perform tolerance stack-ups, from identifying the design requirement, identifying the stack-up problem, assigning preliminary tolerances, analyzing to verify if the design requirements have been met, and then different strategies for making adjustments. The advanced course helps students to apply GD&T to achieve the mating and functional requirements of their products. The course reinforces the fundamentals and provides applications-based exercises where students apply what they have learned. Students gain experience and confidence selecting the right definition strategy for an assembly by working these more advanced application exercises. And they do this with their peers in groups under my guidance in a classroom setting. The full summer schedule of mechanical design engineering courses is on the screen. As you can see, there are many offerings to choose from. If you want to make better drawings, if you want to read drawings better, or even ask better questions about the drawings that come across your desk, QSG's Summer Design Engineering Calendar is here, and there are opportunities for Part 1 or Part 2 GD&T, as well as shorter courses if you just need a primer or an update. For today's webinar, what I wanted to do is to share with you a few stories from my own professional experience in consulting and teaching, and use these stories to drive home some of the advanced concepts. Now, first off, when documenting a part's functional requirements with a drawing, the engineer has to select the features of the part to serve as that part's datum features. They select which features and in which order they apply in order to constrain the part. This becomes the datum reference frame for the part, but datum features have to have tolerances as well. So a very reasonable question is, how precise do they need to be? To determine how precise is precise enough, I present the case of the flexing frame, an expensive part that I was quite eager to produce without scrap and without rework. On this similar but simpler part, the datum features have been identified on the drawing. Identifying which features make up the datum reference frame is not enough. Just because a feature is identified as a datum feature doesn't mean it's produced perfectly or to any degree of precision. Engineers also have to place tolerance specifications on their datum features themselves, which ensure they're produced adequately in order to serve their function of constraining and locating the entire part. Each datum feature has to be qualified, and what that means is for a primary datum feature, we're usually talking about a form tolerance, qualifying the feature to itself. Secondary datum features might require a form tolerance, but they would usually also require an orientation and or location tolerance back to the primary datum. Tertiary datum features would also require orientation and or location tolerances, depending on the feature, back to the primary and secondary datums. Each datum feature is now qualified with an appropriate tolerance. Now, a common feature in the field of machinery design is a planar surface that acts as the primary datum feature for a part. Engineers just love stacking flat surfaces together and attaching them with fasteners. This is very simple, very economical to produce flat surfaces, to produce clearance holes and tapped holes, and fasteners are very economical and they're easy to use in the field. So it's obvious why this is an easy design choice. The challenge is to make features precise enough to do the job, but not so precise that manufacturing becomes cost prohibitive. A rule of thumb that I've seen in other GD&T texts is to set the tolerance for qualifying datum features to be equal to or less than the smallest feature tolerance on the part. For example, with this simple part here, there's a flatness on datum feature A of 0.05, and then there's a functional feature, there's a hole with a 0.2 position tolerance on it. So in this case, this primary datum, it seems to be produced flatter than the rule of thumb would suggest. The actual part in question is more complicated. It's shown here on the screen. This is a redraw of the customer's print. It's drawn upright in its mounted position. The plate on the bottom of the part is 3/4 of an inch thick steel. It's about 300 by 100 millimeters. And the overall height of the part is about 450 millimeters. Now this mounts to a larger support structure for a piece of factory automation equipment. It is strong enough, quite frankly, to hold up a highway overpass, but it actually only supports a couple of lightweight mechanism components. The reason it's designed to be so stiff is because it has very strict vibration requirements. It can't allow the mechanism to flex at all when it's subject to the shaking loads of the automation. Now, there was a concern raised during the design of this part about the tool mounting face, which is shown highlighted in gray. There was concern that whether or not it would be able to hold it accurately if there was any variation from perfect flatness from the primary datum surface. Now, there are some questions that were generated to help answer that issue. Given the flatness tolerance of X and the tool mounting accuracy of Y, how much does X affect Y? How small does X need to be to ensure that the tool mounting face is within Y? And can the required X even be produced? And if not, what else could be done? And these questions help us drive down toward the answer. The problem that we had with this part, at a small enough scale, everything behaves like a mechanism. At the scale of the precision that's on that tool mounting face, even the frame with its 3/4 inch thick steel plate welded construction could not be considered a rigid body. A simple hand calculation was done to attempt to gain some insight into those questions that I addressed. The worst case imaginable was if the primary datum surface was made in the shape of an arc where it touched on the ends and it had the maximum variation in the middle there. The tool mounting surface in question would then flex in position when the frame surface was mounted rigidly with its attachment bolts. I've drawn an angle theta down at the bottom to show the angle that the bottom surface makes to the horizontal. It's not a 0-degree angle. At the end, it's the steepest angle because it forms that arc shape. So just assuming this sort of variation, once the bolts are tightened, that will be flattened out again, and then the tool mounting surface will flex by some amount. So my calculation is shown here. I'm a big fan of the back of the envelope calculation. And yes, I do consider this a simple calculation. I had to look up the formulas to use in a math book, but this type of simple calculation can get me in the ballpark of the right answer. I certainly could have tried to model the variation on the part with finite element software, but at what cost in time to learn the software, to get the model up and running, to debug any problems with the model solving, because I'm not a regular user of the FEA software. And there would not be much benefit to that. I could certainly get a more exact answer, but I don't need an exact answer. I need to gain insight into this problem. And I got some insight into this problem. I found that for whatever variation existed on the primary datum surface would result in a 6 times multiplier in a position change on that tool mounting surface. So this was insightful. A variation on flatness of 0.05 could result in a 0.3 millimeter movement of the tool mounting face. What does that mean to our attempt to make a drawing? Well, if I need the tool mounting face to be located within 0.02 millimeters, I could get that by making the flatness of the primary datum 0.003 millimeters, which was just not happening. So what else could we do? I had to go and look at the drawing board. Now, by default, per GD&T, all tolerances apply in the free state of the part. That is, the only forces acting on the part is the force of gravity. But I can specify requirements in a restrained condition. The ASME Y 14.5-2018 standard that documents GD&T describes this option. The applications are usually suggested for are flexible parts like O-rings. But every part is elastic. Every part deforms under load. The only difference between one part and the next is what is the spring constant. Now, the restrained condition is intended to replicate the condition the part lives under in its service life. To invoke a restrained condition under drawing, we have to apply a note. The standard allows us to write a general note or a local note or a note flag. A general note applies to everything on the print. All the dimensions and tolerances apply in the restrained state. If we want the restrained state to apply to only specific features, then those are highlighted with a local note, like you see on this drawing. This drawing here is a local note up at the interior surface. Between points X and Y, there's a profile with a 2 millimeter tolerance on it. That applies when it's in a restrained state. There's also a larger tolerance, a 5 millimeter profile of the surface between the two datum features. That applies in the free state. So with the note on the drawing, the two different conditions apply for this part. The tolerance on the datum features in the free state, and then an additional tolerance on those two other features when it's in a restrained state. If we want to invoke a restrained state for a part to be inspected under, we would specify the magnitude of the restraining forces, their location, direction, sometimes sequence that they're applied in, what area they apply to, and when it's necessary, we would also indicate the direction of gravity. Now, if all of these requirements for the restraining forces aren't put on the print directly, the Y14.5 standard has some defaults that kick in. For example, when we specify a feature to be a datum feature, if we don't specify the direction and location of the force is applied across the entire datum feature. It's applied in a direction normal to the datum feature. If we use datum targets, the defaults are similar. The forces are applied over the datum targets. They occur over the same area of the datum targets and in a direction normal to the datum targets. Now, when we apply a force to restrain the part is going to deform. That's the whole part. That's the whole point of it. When the part deforms to comply with the datum features, that's the state it's in when we measure it. This example, a second example shown on the screen here, shows what a simulator would look like. It's got some flat planes. The part itself is produced bent. There's lots of variation in that part, but when it's held down against a simulator for datum surface A, it'll become flattened. Another application that's frequently used when a restrained condition is specified is a free state modifier. A free state modifier can override a general note that applies to the entire drawing. And the way this gets used is with the example on the screen. If a general note specifies that all dimensions and tolerances apply in a restrained condition, specific features can be said to apply in a free state by using the free state modifier. With the one shown on the screen, we're using a restrained state for the runout tolerance. However, to check the circularity of that datum feature B, we're inspecting that feature in its free state. So the solution for this part was to inspect it in a restrained state. A custom inspection fixture was built. This was a 2-inch thick ground slab of steel with drilled and tapped holes to mount the part to. Of course, the tool mounting face with the 0.02 profile tolerance, that was finished ground in a similar fixture setup with the bottom primary datum feature mounted to the machine bed on the same surface. So after it's removed from the grinder, whatever residual stresses remain in the part from machining, those are relieved, the part flexes into some other position and deforms slightly. That's okay because we're not going to inspect it in that free state. We're going to bring it to the inspection shop. We're going to mount it to a custom inspection fixture. We're going to force it back into a deformed state, the identical deformed state it was in during finish grinding. And then that is also going to be the exact same deformed state it's in when it gets installed at the customer's plant. So we have this consistency where the part is machined, inspected, and then lives out its useful life in the same constrained state. In summary, we had the part and its primary datum feature simply could not be made flat enough to do its job. So the drawing specified that the inspection had to occur with the part restrained, and the restraint was the same in manufacturing, inspection, and in service. What do we learn from this? Well, engineers have to consider how variation affects the primary datum feature as well as other datum features, and how it affects their ability to locate subsequent features. And inspecting in a restrained state is a perfectly good option. The second story I'm calling the lovable reject. It's the case of a poor rejected part. The part was produced defective. The supplier that produced it didn't realize it was a reject. They did not have the ability to inspect all the features on the part, and I'll show you why. So they made the part and sent it to the customer. The customer's incoming material inspection lab kept a MASAC coordinate measurement machine in a climate-controlled environment. It was a state-of-the-art facility. They picked up on the error. The CMM operator noticed the part was out of spec, but instead of calling foul on the supplier, they gave the part another chance, because even though the part was a reject, somebody was going to love it. This is the part. It's a cam. It was shown to be out of spec. The mechanism is shown in a simplistic form here. The drawing with the key features is included as well. The part failed on the profile of the surface tolerance. The cam operates by engaging a cam follower and produced a translating motion, which was important for the part's function. Now, this is what the part looks like when it's fixtured on its datum reference frame, ready for inspection. The primary datum A is a plane contacting the highest points on the cam's back surface. Datum A simulator is a flat granite inspection plate. Secondary datum B is taken regardless of material boundary, so it is the axis of the largest expanding cylinder that can fit within the actual produced bore, while remaining perpendicular to datum A. The size of that datum B simulator depends on the size, the form, and the orientation of the bore as it was actually produced. Then the tertiary datum C. It's also taken regardless of material boundary, so that datum is the center plane of the widest expanding block, the widest expanding simulator that could be fit inside the actual produced keyway of the cam, while remaining perpendicular to A and while remaining centered on datum axis B. The ultimate size of that simulator depends on the size, the form, the orientation, and the location of the actual produced keyway. So now this datum reference frame was established by inspecting points on the CMM and mathematically defining these planes and axes. The profile was then inspected on the CMM, and that's when this result occurred. The as produced cam the cam picked up points, the CMM picked up points on the cam profile. Those points are interfaced with the 3D CAD model that was used to generate the toolpath, and they can be compared point by point. The CMM software highlights points that have excess material, points that have insufficient material, as well as points that are within the tolerance. Now, as I said, the inspector gave this part another chance. Because the inspector understood how the part was to be used, they unlocked the profile tolerance from datum C and performed a best fit analysis of the inspection points. This creates a profile tolerance zone that's not completely locked down to the datum reference frame. The unlocked profile tolerance zone is located and oriented to datum A and B, but it's free to rotate about datum axis B. By unlocking the profile tolerance zone from the datum reference frame, it doesn't change the shape of the tolerance zone. It doesn't change the size of the tolerance zone. The shape is still the region between two offset curves, offset outward from the basic profile and offset inward from the basic profile. So there's some text. They created that unlocked profile zone and performed a best fit. The best fit algorithm allows them to calculate a rotation angle. So they determined that the ideal angle of rotation, if the profile zone was rotated by 0.2 degrees about datum B, then all the points fell within the tolerance zone. So this was an interesting finding. This speaks to a very particular type of variation that was produced when the cam was made. And this shows the inspection results for the best fit part. So now the question goes up to the engineer. Is this part acceptable? And to answer that, we have to start by understanding the application a bit better. Here's the cam in its application again. It's driving the pink follower up and down. It's held on a camshaft through its precision bore. There's a keyway to transmit torque from the shaft to the cam. It's clamped axially to the shaft. And up at the top end, what I've removed from the picture is an end of arm tool that is driven by this cam. It's driven through a specific desired motion path. Now, one end of arm tool or several end of arm tools driven by similar cam mechanisms will interact to perform some mechanical operation. What is the cam's job description? Well, it's to position the end of arm tool where it needs to go. So let's dig into that job description to try to figure out, does variation hurt the cam's ability to do its job? Now, by unlocking the measured data from datum C, we essentially shifted the entire displacement diagram by 0.2 degrees. A displacement diagram is a standard issue on a cam drawing. It shows the relationship between the cam profile and the motion that's needed. You can see from the displacement diagram, the horizontal axis goes from 0 to 360. That's all the way around the cam. And then the end of arm tool position is shown here. So by rotating the profile, that's essentially shifting the entire displacement diagram. And now we need to understand what effect this has on the end of arm tool. Because the cam creates a custom motion profile for the end of arm tool, the effect is different at different points in the cycle. At point A in the cycle, any rotational error in the cam's position has no impact at all on the end of arm tool's position. At point B, however, a 1 degree change in the cam angle translates to about a 1.2 millimeter difference in the end of arm tool position. So this is really the maximum sensitivity that the application has to the cam angle. Now, the end of arm tool in the middle, the end of arm tool position in the middle of a move is not as critical as its position at the high and low dwells, point A and then the high point. And there's more than enough clearance during the moves to absorb this position error. So as the graph shows, the position error per degree of rotation is the slope of the curve. That's maximized at point B and the point across from that. And it's 0 at the dwell positions. So because of the way this cam functions, it allows some rotational position error without impacting the performance at all. So the drawing should be revised to allow this part to pass inspection, as well as any other parts that are made with a similar variation. Now, we want it to relax the specification somehow. So what's the right strategy for doing that? If we added a at maximum material boundary modifier to the datum reference C, this would allow exactly the type of datum shift that we want to have. Now, normally specifying datum C at max material boundary for this part would allow some datum shift. The exact amount depends on the actual produced keyway size. The part would be able to rotate slightly within the clearance between the keyway or the datum simulator and the actual keyway. So how much can it rotate if we specify it at maximum material boundary? Well, we need to piece apart that 10 J9 tolerance. If we look up the tolerance that applies to there, it's plus or minus 0.018. We calculate the maximum material boundary for datum feature C and we get 9.952. So that's the size of a simulator that we could use. But we don't really know if that meets the design requirement. That's just the size of the simulator. The two options that I've talked about so far for the datum reference frame are shown. There is a third option. And we can have a fixed size simulator or a fixed size boundary for datum feature C, which is any number. It doesn't have to be the max material boundary. So after considering the application and the application of similar parts, a simulator was desired that would allow up to 1 degree of total cam rotation during inspection. So a calculation showed us that this amount of rotational variation translates to a boundary size of about 9.8. Now, subsequent cams that would be designed after this one, they would all be designed with an explicit guideline that says they have to permit 1 degree of rotation and still function acceptably. So this was an acceptable amount and allowed us to allow more variation during manufacturing. The feature control frame that references datum C at a custom simulator size is shown here. 9.8 is the simulator size that's used. So in summary, the part was marked for rejection during inspection, but the inspector suspected it might be good and conferred with the engineer. The engineer confirmed the part was good as is, and the engineer made a drawing revision. The datum shift allowed the engineer to specify exactly the type of geometric control that the application required, without overly restrictive control that didn't produce any benefit. So the tolerance was loosened, and there are many ways to loosen the tolerance. It's not always about making the tolerance number larger. Datum shifts, bonus tolerance, composite feature control frames, these are just a few of the tools that engineers have to relax requirements that can be difficult to produce, but don't have any impact on function. So for my last story, I ask a question, is a B good enough? When creating drawings, engineers need to be careful with their choice of dimensions. Recently, a part was designed, detailed, fabricated, and inspected. During the inspection of a batch of 173 parts, an unusually high number of rejects were found. Out of all the parts that were, once all the parts were inspected, 28 of them were out of spec, leaving about 85% of the batch good. An 85% pass rate in school will get you a grade of a B, but in manufacturing, it is not acceptable at all. So I was asked to dig in and try to find out why. Here's a redraw of the part, a simplified redraw of the part. I've highlighted the datum features and some tolerances that apply. The part is a precision ground slide body that engages a precision ground housing in order to provide a linear translating motion. Additional components are attached to the slide body by 2 dowel pins that are press fit into the diameter 3 K7 holes. The inspector started checking the position of those 3 K7 holes, and a trend began to emerge. All of the holes were shifted downward in this view from their target position. Now, datum C provides a reference for left and right location. That's the 18.5 and 28 basic dimensions. Datum B provides the reference for vertical dimensions, so dimensions in the up and down location. Now, it appeared from the inspection results that all the holes were shifted by about 0.01 millimeter from their basic location. This had the effect of pushing 28 of them out of the tolerance zone, rejecting 28 parts at a cost of about $100 each. We see here the measured and plotted locations of 173 holes. And they're drawn relative to the datum reference, relative to the position tolerance zone. The holes are clustered about 0.01 millimeter off target, or about 12.5 millimeters from the external face of the part. Little educated guessing can tell us what probably happened with these parts. Now we know that we can see that the distribution of holes is a nice tight distribution, so we probably can't blame random cause variation for these rejects. It's a repeatable shift in position of the holes that leads us to either a repeatable setup error or an incorrect target position that affected all the parts. Now here's the drawing again. We see that the hole on the right is on the drawing center line. This center line represents datum B, the center plane of the 25 millimeter feature. The 25 millimeter overall width has a tolerance of minus 0.013 to minus 0.026. Because the hole is shown on the center line and its position is controlled with a feature control frame, that means that a basic dimension of 0 between the datum and the hole exists. The 0 basic dimension is implied and doesn't need to appear on the drawing. However, if we keep looking, we find that there is an additional basic 12.5 millimeter dimension locating the hole from the top face of the part. This dimension is actually redundant and shouldn't appear on the drawing. A basic dimension locating the whole center line can't originate from the top surface. We don't have a basic dimension that defined the top surface. The top surface of the part is controlled by the size dimension, not by basic dimensions and profile controls. The basic location of the hole needs to be dimensioned from the datum reference frame, and the exterior surface of the part doesn't count. The datum B is the center plane. That's where the dimension needs to originate, not the top surface or the bottom surface for that matter. Now, basic dimension could be drawn from the center plane of the 25 width feature to the center line of the hole, but that dimension value would be 0, and so it doesn't actually need to appear on the drawing. Now, the overall width of the part was inspected. It was very consistently between 24.976 and 24.982 with a mean value of 24.979. So it's an undersized part and it's being made with the right width. The vertical dimension to the hole was given as 12.5 on the drawing. This was halfway through the nominal width of the part, the width that the CAD model was made to. The model was made to 25, that's the nominal size, and you pull the dimension halfway down, you're going to get 12.5. Now the actual target for the whole hole is halfway in the middle of the part. It's where datum center plane B is. Because each part is made slightly different, the distance from the top surface of the part to the hole is going to be a different target. It's going to be slightly different from part to part. For the average part, this half width was about 12.4895. So I believe the machinist targeted a location of 12.5 from the outer surface, regardless of the actual width of the part. This would place the hole about 0.0105 off target, depending on the actual produced width of that part. Now, this is a very small difference from target, but given the size of the position tolerance, it was enough to throw 15% of the parts out of spec. Did the machinist make a mistake? Well, it's not the person, it's the process. The manufacturing process was flawed. The machining process targeted the wrong dimension. The drawing creation process was also flawed. The drawing creation process allowed a redundant and a misleading dimension to appear on the drawing in the first place. Now, a mechanical print depicting a component to be produced is a powerful document. Releasing that drawing to downstream process initiates action. Before the design release, the part only exists in the imagination of the engineer. But after design release, now it becomes real, and it becomes real work for lots of people. Planners procure material, machinists start setting up CNC equipment, inspectors begin measuring. So there's a lot of processes along the way that follow from that released drawing. And if that drawing contains a mistake, then those processes aren't going to work out well. There are a lot of steps to the manufacturing process. There's more than enough steps that incurred some sort of failure. When you think about what happens from the drawing creation step onward, many people are going to look at that drawing before it results in an inspected part back in the customer's plant. Everybody that drawing touches along the way has an opportunity, has a responsibility to fully comprehend the drawing, to make sure that they're not acting on assumption. Every step in the process needs to have a feedback loop back to the engineering department. If there's no feedback loop, then the process is flawed. Now, I can understand the hesitation in pushing back, asking questions about drawing. After all, drawings are checked and verified before they're released. They're not supposed to have errors. When you see something potentially wrong with a drawing, it always creates doubt whether it's the drawing that's wrong or whether maybe our own knowledge is lacking. Who's truly confident enough in their own knowledge to start a discussion to try to clarify a print, what could be a drawing error or a gap in your own knowledge? No one wants to start giving critical feedback and then having it turned back on them and being told, no, it's actually you who's wrong. In some cultures, particularly, it's completely unheard of to question someone who is perceived as at a higher position in the company, as engineering might be perceived. And all this is before we even think about the time involved. Even if we question a drawing and get the clarification that we need from the engineering department, how long does this take? Shouldn't we just keep the work moving along and not hold up the process? Well, in my opinion, it's always better to ask. The benefits of getting our documentation packages right outweigh the cost in the time of asking. If we approach a drawing review discussion with an attitude of respect and teamwork and learning, there's no risk of bruised egos. These discussions usually go very quickly too. Engineers, machinists, inspectors, they're all collaborating to get parts right. The more we work together and the less we treat engineering as a toss-it-over-the-wall function, the better it all works. Now, I believe that as an engineer, it's most important to get the feedback all the way back up the line to me. Since I'm originating drawings, the problem drawings don't go away. They don't get changed unless somebody actually changes them, unless I get the feedback. So with this third example, a drawing was released. It had a redundant and a misleading dimension. The machinists tried their best to follow the drawing as they understood it, but ended up producing many rejects. The inspector who noticed the trend in the produced parts figured out the reason. A quick conversation with engineering confirmed that the 12.5 dimension didn't need to be there. Reviewing the drawing, only that one dimension needed to be removed from the print to make it a good drawing again. So an engineering change order was submitted to get this dimension off the drawing. Now, the customer had a good internal process for getting questions answered, getting feedback back to the engineering department. But the supplier was not involved in that process. So as a result, 15% of the order had to be remade. The customer had to pay for it. Their drawing was an error. The supplier was able to argue that the drawing error absolved them of responsibility to eat the cost. So everybody needs to have a mechanism in place to get feedback when there's a question. Now, how do we summarize what I talked about today? I finished by showing some of the rules of GD&T. These rules are all written down in the standard. Now, I summarize here to highlight the ones we've talked about. The document's a bit strange in that rule number 1 and rule number 2, they're written in different sections. They're described separately. They're not part of a numbered list. The remaining rules are called fundamental rules, and they're organized by letter. Don't ask me why. I wasn't on the standards committee meeting at the time. I assume there's some history behind it. Now, these rules, they don't seem all that advanced, but the trick is in recognizing them in context and applying a deep understanding of each of these rules to make good drawings. With the first case I talked about, is a B good enough? We saw fundamental rules C and L. Excuse me, the last case, C and L. The lovable reject, we saw rule number 2 being applied. The datum is specified regardless of material boundary by default, but if we don't like that, we can change it. And finally, the case of the flexing frame also included fundamental rule N about drawings occurring in a free state. And when we don't want that, we can change it as well. I add my own rule to the list that I call Rule 0, just so it makes it to the top of the list, and I think it's an important one to remember. In Rule 0, some drawings are bad. Now, I emphasize Rule 0 because bad drawings result in bad parts, costly rejects, delays for parts to be made, and delays for drawings to be revised. But these are only the costs that are easy to quantify. Most of the costs are actually hidden. Bad drawings make everyone who sees them question their own knowledge of GD&T. This is the language, and learning any language is hard. Looking at prior examples, prior drawings, is a great way for people to learn. What happens when those examples that we're learning from are actually bad examples? Our learning slows down, we lose confidence in ourselves and our learning, or worse, we pick up bad practices and false information. We create bad drawings and we perpetuate them. All of the downstream processes are affected by this, from purchasing through manufacturing through inspection. But engineering is a downstream process too. Engineering is the downstream from the prior product that the company introduced, from the last project that the engineering department worked on. We build off what has been done before us, and sometimes even when it's wrong. We perpetuate bad drawings when we don't recognize them for being bad. In each of the 3 case studies I presented, a drawing was revised at the end. It wasn't good enough to simply accept a part that should have passed inspection in the first place, or to remake rejected parts that somebody tried to make from a bad drawing. This would not have fixed the root cause. The root cause was the drawing, and if the drawings weren't fixed, those problems would keep coming back. If you like to make better drawings or to read drawings better or ask better questions about the drawings you see, QSG's Summer Design Engineering Training Calendar is here again. There are plenty of opportunities for Part 1 or Part 2 of GD&T, as well as shorter questions if you just need a primer or an update to the latest standard.
All right. I believe we'll end things off here. So thank you everyone for attending. If you have any follow-up questions, please reach out, and I hope to see you in our future webinars. Thank you, Charlie, for a great presentation.
Thank you.